So this is the rectifiers and smoothing problem sheet for EEE118, and we'll begin with question 1, which says, in the half-wave rectifier circuit of figure 1, both the diode and the transformer are ideal, i.e. deconduct with 0 voltage drop for forward bias and is an infinite resistance for reverse bias, and the transformer has 0 series resistance. Sketch the shape of the voltage VO as a function of time for at least one period of Vs. What is the peak value of VO? What is the average value of VO? What is the RMS value of VO? What is the power dissipated in R? And then, if the transformer has a total effective resistance of 10 ohms in series with its secondary winding, what is the new peak value of VO? And what is the new power dissipated in R? So the circuit looks like this. We've got some output and resistor in parallel with the output. There's VO. And then we've got diode. And then we've got transformer. And this is Vs, and it's 9 volts. And the resistor value is 100 ohms. So the first thing we can say is, well, question tells us this diode will switch on with no volts across it, so what we're after is a situation where we have more than 0 volts in that direction. So the question then becomes, well, if we put sine wave in, when's the first time that happens? So we can draw a graph. And the graph, sine wave input will look, I should do it dashed. Bit like that, and there'll be some peak values. Which I've got there, and this will be, we'll call this Vs, and this is time, obviously, and we'll be able to say that this is 0, and this is pi upon omega. And this is 2 pi upon omega, where omega is the angular frequency, which is 2 pi times f. And the period, or the distance between there and there, should be 20 milliseconds, or 2 pi radians, if you prefer. And the equation for this line is Vs is equal to Vs peak sine omega t. I could say plus phi, but phi is the phase shift and it's 0 at the moment, so sine omega t will be sufficient. Yeah. So then the next thing is we have to sketch the output. We haven't done that. So output I'll do in green, because that's my usual one for voltages. So this is rising here. This voltage is rising. So this end is becoming, or rather this node here is becoming more positive than the reference. And the reference in this situation is all this stuff here. So all this bit is getting higher than this bit. So let's assume the diode switched off. If the diode is switched off, then there is no closed conducting pathway because the diode is taken away from the circuit, and an open circuit is what replaces it. So there's no current flow because the diode is not there. What will the voltage be across the diode, or where the diode would have been, if this end is getting bigger with respect to this end of the transformer secondary? Well, this is getting bigger, there is no current flow, so this node must be at the same potential as this node, because there's no current to flow through the 100 ohms, so there's no voltage dropped across it, so this node is the same potential as this node. So across the open circuit, we don't actually have that direction, we've got a voltage in that direction where this is the more positive end and that's the more negative end. So that's a situation where the diode is reverse biased, which means it's not going to conduct. So for all of this period, this half period here, this region, we have an output of 0. But then when we get to this point, we'll be in a situation where there is no voltage across the diode, but this voltage here will be in the falling part, so it will be falling below 0. And when it does so, this end will be more negative than all of this stuff, and since there's still no current flowing at this point, because we're on the 0 point, this node here, the output node, will still be at the same voltage as the reference, because there won't be any current flowing through R, apply Ohm's law, no voltage across it. I times R is 0 times R, doesn't matter what R is, still got nothing. So that will be the point where there's no voltage, but as soon as we drop below the line, down to this region here, a voltage will appear across the diode like that, and the question tells us that this diode will conduct when there is more than 0 volts anode to cathode. So that's the situation. As soon as we cross this line on the blue dash sine wave, as soon as we cross the axis, that's the situation we'll be in. This will be more than 0, and we'll end up with conduction. And there is no voltage dropped across the diode, so whatever our input is must be whatever our output is as well. And the reason is we've got some current conduction down there, down there, down there, up there, around there, and through there. Okay, so conducting some current, and this voltage is 0 volts higher than this voltage. So this is our Vs, which is a maximum of, or RMS value of 9. And a maximum value of Vs peak, or I think we'll just call it V peak if you like. So no voltage dropped across here, so this must be whatever that is. So that's why the green and the blue overlap each other here. And that's our graph of the output. And that is, well, I say at least one value, that is exactly one value. So if we had another one, then we'd have to keep this going down here for a bit, and our next output would be nothing because the diode will stop conducting when we get to the 0 point here, because the current, not because there'll be the wrong voltage across it, it will be because the current ceases. And then we'll begin all over again, and that would go off into another sine, or another negative half cycle of a sine wave. So we have to, next thing it asks us to do is, what is the peak value of VO? Okay, well, VO is in green, so I'll do this in green. And the peak value is just here, and this is, we've got an expression for this, it's V peak sine omega t, and the sine omega t bit does the shape, and the V peak is the bit we're interested in, so this is actually minus Vp. And you really ought to know that for a sine wave, the relationship between the RMS value and the peak value is root 2. So we've got V peak is equal to root 2 times Vs. And that is 9 times root 2, which is, quick calculation, root 2 times 9, 12.7279. And the next digit is a 2, so we won't round it up. This is volts, obviously, and we've got to be a bit careful because it's actually the negative peak. So this is actually minus 12 that we're interested in. So that's the value there. If this question said 0.7 volts across your diode, you'd then subtract, or sorry, you'd add 0.7, and the line would go like that, and there'd be, your gap here would be 0.7. But that's not what the question asks, so we won't worry about it. So we can actually write this on the graph as well. It's minus 12.72, or 73 if you like. Okay, that's fine. So the next thing that we're asked to do is find the average value of VO. Now, you can either remember that the average value of this particular shape is V peak over pi, if you prefer. That's fine. It's not really satisfactory though. It would be much better if you could derive it. So we'll do that now. I hope you can see that the average value of the whole sine wave would be 0, because there's just as much stuff up here as there is down here, assuming this keeps going forever. But the average value of the half-wave rectified sine wave is not 0, because there's an imbalance of stuff above and stuff below. In fact, there's nothing above and everything below. So not only is it definitely below the line, it's probably about, more or less, about there. Because what I'm looking for now is all this stuff here and all this stuff here to be broadly equal in area. That's what would deal with it, it's the equal area. But you can't just draw a line and go, oh, it's about there. That's not enough. Not for engineers. So we need to do some deriving. And I'm probably going to do it in black because my green pen's a bit weak at the minute. So we can say, well, we know that this point is pi upon omega, and we know that this point is 2 pi upon omega. So what we can say then is, well, we need to know what the area under here is, and then we need to divide it by the period. Now, the period is from there to there, but we only have to do the integration across this bit between pi upon omega and 2 pi upon omega. And the reason is this integration is definitely going to be 0. So as long as we deal with the full period, we don't have to worry about this bit because we know it's already 0. There is no area under this green line at all. So we can say that V average is 1 upon t, t being the period, so I better write that on as well actually, hadn't I? So t equals, and t is period of waveform. And t is equal to 2 pi upon omega. So So you can see this length here and that point there. So 1 upon t times, and then it's the integral. Now, you might be tempted to go 0 to t stuff. Actually, we're not going to do that because we'd have to do 0 for the first bit, and then we'd have to do the sine wave for the second bit. But what we can say is actually, the green line and the blue line sit on top of each other. So we'll integrate the blue line, but between this point and this point, so we won't actually worry about this bit. And that means that we can perform the integration on this expression, which is really handy, because writing out an expression for the 0 and then that bit would be a bit more complicated. We have to do it in 2 different parts. So we can use this expression and just be careful about where we do the integration over. So we'll do it between t over 2 and t, which is the second part of this the second half cycle of this waveform. So this is equals t over 2, and this is equal to t. But you already knew that because t is down there and that lines up. And then it's Vp sine omega t dt. So that's the integration we've got to perform. And the first thing we can do is sub in for t what the actual values of the graph are. And I'm going to rub this out, and I'm going to rub that out and write it up the top. So we've got a bit more room. So we had Vav is 1 upon t integral t upon 2 to t Vp sine omega t dt. Lucky it wasn't any longer, it wouldn't fit otherwise. So the next thing we can do is substitute in for t. So we'll have Vav is equal to 1 upon 2 pi upon omega. Integral between pi upon omega and 2 pi upon omega. And we haven't subbed in anything else yet. So this is still Vp sine omega t dt. So we'll perform the integration, but we won't insert the start and end points. So we'll have Vav is equal to, now this being the 1 over t, right, so 1 over 2 pi over omega is omega over 2 pi. Essentially you flip the denominator bit, so it's omega upon 2 pi, and then we'll have some square brackets, and we'll have minus Vp upon omega, so it's minus the a upon the, well, I would think about this as a sine b and then parameter, and the parameter is what you're integrating across. So you'll end up with minus that over that, cos. If you're unhappy about that sort of thing, you could in principle look it up in a table of values, or a table of integrals, but in the examination you won't get a table of integrals, so you'll need to learn them. And you can either learn them by rote or learn them by practice, or make up some rhyme or whatever you fancy, but you must commit them to memory. And this is now our start and end points. And then we'll have to actually insert, so we'll expand this bracket and insert first t is equal to pi upon omega, and then subtract t is equal to, so the same result but with t substituted in for here, and that will yield minus Vp upon 2 pi 1 minus 1, and that is secret. So this is 2 essentially. So the 2 that's here and this 2 here cancel to leave you with minus Vp upon pi. Now, to get from this bit to this bit, it's just your regular integration. You end up, I'll rub that line out and I'll expand that just so that you can see what's happened if you're unclear. You have omega over 2 pi, and then we'll have bracket minus Vp over omega cos omega pi over omega. Oh, nearly. So that's our first condition, and our minus second condition, minus Vp upon omega cos, and this is 2 pi upon omega. Oh, sorry, it's omega 2 pi upon omega. So we have an omega there. Do that again. I've missed an omega out because we've got an omega here, and then we've got a 2 pi upon omega, so the omegas will cancel again. So we've got omega, and it's 2 pi over omega, and that's all cosine. Then we need the big bracket, then we need the square bracket. So that's what you're actually doing, and all this bit will boil down to 1, and all this bit will boil down to minus 1, which is how you arrive at the line below, which was minus Vp upon 2 pi, 1 minus brackets minus 1. So it's, if you want to, you can put that in the bracket as well, and that would represent that bracket, and these two would represent that bracket, and then you have that bit there. Right, okay, if you're wondering where this omega goes, it cancels with that omega and that omega. And that omega and that omega cancel, and that omega and that omega cancel. Now cos of pi, you can pop in a calculator if it's on radians, and cos of 2 pi you can do the same with, so you can get the values for those, and that's where that drops out from. Alrighty. So then the only thing you've really got to do is actually put a value in. Or put some values into your calculator to get the answer. So we'll do that quickly. It's minus Vp upon pi is what we had, and minus Vp is 12.73. So it's minus 12.73 upon shift pi minus 4.05. So just for completeness, we have is equal to minus Vp upon pi for this situation. Vav for a half-wave rectified sine wave is not always this, it's only this particular one. If we'd had a 0.7 volt diode drop instead, you'd get a slightly different value, and if it was the diode was the other way around, the minus would be disappearing from here. But anyway, for this situation, minus 4.05 21 volts. So it's important that you know how to derive that sort of thing, because just learning some standard results, there are more different circuit types than there are people or grains of sand or galaxies or whatever, and you can't know all the situations. You just have to know how to get the answers that you want for a particular situation that you're facing, and that means having some tools at your disposal, one of them being mathematics, to actually derive the things you need. You can never remember everything you need to know. It's just not possible. So that's the solution for part 3, which was what was the average value of VO. The next bit asks, what is the RMS value of VO? It's the root of the mean squared. So first thing we have to do is VRMS is something square rooted. which is raised to the half, or you can put a big square root round if you want to. And then we've got to do, so it's the root of mean squared, so the mean squared value. So we're going to have to square the value, then get the mean of it, and then root it. So in math speak, that's root is the outermost thing, mean is the next thing, square is the middle thing. So the next thing we're expecting is a mean, and we know that to get a mean we need 1 over t integral across one period of whatever it is dt, and in this case the whatever it is will be squared as well. So we'll have integral across over 2 pi, which is 1 over t, where t is that, so I've already done the 1 over t thing, and it's just caused this equation to flip. And then we'll do it across the same period, same half cycle that we've done in the past, because the only bit we're interested in is this bit. This bit we know will come to 0. It doesn't give us anything extra. And then we have to do vp squared sine omega t, and where are we putting the square? Sine squared dt. So this is the squared bit. So this is squared. This is the oops. Oh dear. This bit here is the mean bit, and this bit here is the root bit. And as long as you can write an expression, you can use this. So you don't have to worry about what mean squared values are and taking averages and that sort of thing. If you can't fathom your way through it by going, well, I know what the averages are, not the mean squared bit is because I can square the root mean square, and so on and so forth, you can just blindly apply the RMS equation, as long as you can do the integration. So we can get a value. I'm not going to do the integration, but if you can do the integration for the average, which I just demonstrated, it shouldn't be too much of a stretch to do this. If you're worried about integration sine squared, you can just look it up in a book or try your favourite search engine, but ultimately you should know how to integrate it. Right, oh, I missed an equal sign, didn't I? There's an equal sign. What is the power dissipated in R? Okay. So let's get rid of our RMS equation. And we had a circuit which is now gone, but it was a transformer secondary with a diode and a resistor, and this was that was 9 volts RMS. So to get the and this was 100 ohms, and that was V out. So if we want the power, we can do P is I squared R, or we can do V squared over R, or we can do IV if you can be bothered to work it out. And does it say the peak power? Just as what is the power dissipated? Right, well, if we want to know about power, that means average power. There is no such thing as RMS power, it doesn't exist. And for average power, as far as signals are concerned, we use RMS values. So RMS voltage times RMS current equals average power. Alternatively, you can do RMS current times resistance equals average power, or RMS voltage divided by resistance is average power, but it's always average power. There is no such thing as RMS power. So since I've got RMS voltage at my disposal already, I'm just going to pick that one, and it's 9 squared over 100, which is 81 over 100, which is 0.81 watts, which is fine, but that's not actually the right answer. That would be the right answer if we had the full sine wave. We've only got half of the sine wave. So if you're prepared to accept that half of the sine wave develops half of the power, and the other half of the sine wave develops the other half of the power, then we ought to be able to say, for this particular situation, actually it's half a sine wave, so divide by 2, which is 0.405 watts. And if you want to do that bit at the beginning, you can say it's v squared upon 2r. If you wish, that's fine. It makes no difference. It's just how you think about it. Alrighty. So that's how you would arrive at that. And the important thing is not to forget the 2. Of course, if it wasn't exactly half a period, it wouldn't be a 2. It would be something else. So we've got part V, which is the power dissipated. The next part of the question says, if the transformer has a total effective resistance of 10 ohms in series with its secondary winding, what is the new peak value of V0? Okay, well, let's draw the circuit again, but this time with the extra resistance attached. So what we're saying is that the diode has to budge up a bit because we've got a resistor in there, and then the diode, and this is 10 ohms. Right, this is nothing more than a potential divider in disguise, because the transformer secondary is just behaving like a voltage source. The diode is on for all of this period here, which is the interesting bit. So it's on and there's no voltage across it. Well, that all boils down then to a source of sine wave energy with 9 volts RS and 10 ohms and 100 ohms. So with a bit of luck you can see that you either go, oh, this adds up to 110 and that's 100 over 100 plus 10 times 9 times root 2. If you want, that's fine. You could just say, look, the denominator here is 1/11th, or rather the fractional parts here are 1/11th. This bit gets 1/11th of the whole lot, and this bit gets 10/11ths of the whole lot. And we know what the whole lot is because it's minus 12.73. So we could do what's 10/11ths of 12.73. That'll give us the answer, no problem. So 10 over 11 times minus 12.73 is minus 11.573. Fine. If you don't fancy that, and you really do want to do the maths, or what little maths there is, you'd say, well, it's 9 root 2 multiplied by 100 over 100 plus 10, and that would give you 9 times the root 2 times 100 divided by 100 plus 10, 11.570. Oh, I missed the minus, didn't I? So 11.57, which is what I had down there just now. So that's how that one's dealt with. And then the next bit is what is the new power dissipated in R. Well, since you know what the peak voltage is, you can get back to RMS voltage. So it was 11.57, I think, but I'll do it again anyway. 9 times root 2 times 100 divided by 110. 11.57. So that's 11.57, and this is peak. And I would like RMS across here. So we'll divide by root 2, and we'll get 8 points, so it's equals 8.181, 81, etc., etc. This is RMS. So if I know it's RMS, I can do V squared upon 2R to get average power, which will be squared upon, and it's 200, 0.334 watts. Run out of space. Watts. There we go. Which is, it's actually 3347, so this should round up to a 5, because the next digit there is a 7. So that's how that one's accomplished, and that's actually the end of question 1.